There we go. Hey, now it's right on here. All right. Hi, I'm Eric. Yay. All right, I'll tell you, I have to start off a little bit here. So I've been doing this for 15 years now. And first 10 years, I worked for just Multnomah ESD. We covered about 40,000 ADM, mostly metropolitan, medium-sized districts. Once we started the CTA thing, for the last 5 years, we're now covering about 260,000 ADM, split between small, medium, large districts, both rural and metropolitan. So, you know, my job's changed a lot, right? Seeing way more variety than I've ever seen before. And our aggregated traffic has been growing at 85% per year compounded for the entire 15 years I've been working in education. I have a degree in economics, and I worked in the banking system before I came here, so I kind of look at these things a little differently than the typical tech person. So I'm going to throw like a lot of math at you, and hopefully we'll go through it really fast so I won't annoy you too much. And I'm mostly going to talk about theory, a little bit of practice, and I really hate giving formal speeches, so I'm going to try to rip through as fast as I can and hope you have lots of questions, because I like doing that, okay? So feel free to interrupt me. Frequently, often ask lots of questions, please. Otherwise, we're getting out of here early, which is not bad, because I hurt my back really bad, and I'm very looking forward to hitting the bar after this. All right? For the record. All right? And again, if I start crying and curl up on the floor for just give me a minute, I'll be back. It'll be all right. Okay, so now that I'm covering so much territory, this is a really hard problem, because what you want to look at for redundancy for a small district is bigger than a big district versus someone like myself is now covering this wide variety, right? Every layer, you're kind of doing things different. So there's really no one good way of giving this presentation. And you can't, the techniques you use for different size districts are different, so you can't really, like I said, there's just not one size fits all, right? But there's some universal aspects to this. One is when you're kind of looking at like redundancy and that type of thing, there's a little bit of a balance there, right? If you have too little or too much, or both can be harmful. If you don't invest enough, you're gonna have outages, it's gonna be unreliable, you know, people are gonna be mad at you. You invest too much, then it's either not gonna be sustainable, or you're draining funds from the classroom that's not really buying you anything, but you know, sucking the money dry that we've better spent elsewhere, right? We're basically fixed income. It's not like we get more revenue if we overbuild our networks. So it's not necessarily a good idea. Get the basics right first, right? If we're talking in terms of redundancy, if you do something poorly and you try to make it redundant, it's gonna be twice as poor, right? You can make a really big mess. And also, redundancy is risky, right? The more stuff you got, the more it's gonna break, the harder it is to fix it. And that's one little dirty truths about this is you think, oh, I have to have redundancy. But if you don't do it right, you're worse off than if you have no redundancy at all. Not very popular telling that to people, but it's true. All right, basics. You gotta think of the whole picture, right? Chain's only strong as the weakest link. And the most common problem we get with people calling up going, my network's broken, are really, really stupidly simple things. They have a single DHCP server that stops responding, no one gets leases, their network tanks, right? That's probably like been problem number one. Same thing with DNS servers. It's really easy to have 2 DNS servers. Have 2 DNS servers. Authentication, dual power supplies in your servers. This is all really, really easy stuff. Do it, okay? There's some really simple tweaks that can save the day, and as you're going through and working on your equipment, think about these things, right? Wireless, for instance. I see a lot of times that school districts will plug all their APs into one switch in the wiring closet. What if that switch fails? All wireless is gone that entire wing. If you have 3 switches, just split them between them, so if you lose a switch, you only lose 1/3 of your APs. If you have sufficient capacity, everyone will just fail over the other APs, and it might be slower, but at least it's still working. And it's really simple, it doesn't cost you any more. Just think about those things. All right, I really love this one. Brian Kerrigan, guys, if any of you guys are old school programmers, you ever heard of K&R, the C book on how to program C? This is the guy that wrote it, right? And he says, everyone knows that debugging is twice as hard as writing a program in the first place, so if you're as clever as you can be when you write it, how are you ever gonna debug it? Same things with networks, servers, that thing. If you make it as complex as you can, where you're just at the edge of your skill level, you're never gonna debug it. When it breaks, you're gonna be screwed. You're gonna have a big outage, you're not gonna know how to fix it, you're gonna have a bad day. And this is my other big problem that we get, is make sure your equipment and your circuits have sufficient capacity. Also happens all the time that, one of the problems we've got, let's see, I won't jump ahead. Okay, quick detour of the art of guessing, right? Especially when we're talking about capacity and failures and that type of thing, we're always trying to guess into the future. And my favorite is a Fermi approximation. I'm gonna use this a lot, that when we're trying to guess, we don't have to really be 100% accurate. We just kind of have to have the right number of zeros. It gets us in the ballpark, and if we're in the ballpark, we can play the game. If we're too high, we're too low, we're not in the ballpark, we're screwed. And it's really pretty easy to do. And the other thing is, if you're uncertain about the future, the easiest way to predict is to take a point in the past, the current, draw a line, and odds are you're gonna hit that line in the future, right? Because things really don't vary that much. So if you don't know, just do what you did in the past, right? It'll probably be okay. All else fails. If you're gonna guess high, right? Because if you're wrong on the high side, you're just spending too much money. If you guess on the low side, you're not gonna have enough capacity, and your network's gonna tank, and it doesn't matter, you're just gonna screw yourself, right? Catastrophic failure, and or hedge your bets. So if you don't know, you can take your best guess and make sure you have a backup plan, right? A plan B in all of this. All right, now we'll get into a little bit of math. Calculating future capacity, right? Because this is the biggest problem I see, besides the simple stuff, is that at 85% compounding rate is an exponential. People cannot do exponential math, right? So if we're growing somewhere between 50 and 100% per year, here's a couple really simple tricks, right? All you have to do in the short term, if your usage is less than half your maximum capacity, you're probably okay for one more year. If your current usage is equal to or less than half your maximum capacity, you might have a problem. Look at it very, very carefully, right? The other way that's kind of neat, when you're trying to decide, you're gonna buy a piece of equipment and you want it to last 5, 10 years, or you're buying a circuit or something like that, and you want to make a prediction that far in the future, the best bet you can do is just take whatever your current usage is, and every year multiply your current usage by 10, that'll get you in the ballpark. Very simple, just do it, it'll be pretty close. If you think, hey, I'm gonna double and it's gonna last forever, you're gonna lose, right? This is kind of cool. This is actually how the math works. It's really easy. It's a simple formula where you just have to take your current usage, multiply it by 1 point, the percentage, and to the power of the number of years you want to predict, right? So it works out that if you're currently using 100 megabit, in 5 years, you're going to be using about a gigabit. And it works backwards too, if you want to look at your historicals, and we'll get to that in a minute. I'll show you what that looks like. And one of the cool things on Google is you can just type that in. Right? If we want to calculate it, we can just do like 10 times 1.6. We're doing 10 megabit, 1.7, and let's say 10 years into the future, right? So if we start with 10 megabit, 10 years in the future, you're going to be using about a gigabit. And that's kind of where it comes up, where the math comes in, where if all else fails, every 5 years you're just at a zero. And that actually matches what the exponential math works out to be. Okay. Oop. The other way of doing it is this fancy one. If you want to predict how long something's going to last rather than trying to guess, it's merely log of 1 divided by your percent of capacity divided by log of 1 percent of growth rate, and that will tell you. Trivial, right? All right, so here's a practical example, and this is real data. It lines up perfectly with when I first started 15 years ago, we had just finished moving from 56K frame relay to T1s. That's 20 times the capacity we're using. It's gonna last forever, right? How long it really lasts? I punch it into my formula, it comes out 5 years. 5 years before we ran out of bandwidth. Right? So let's say, okay, not gonna last forever, but let's say I'm really good at T1s, and I'm gonna be hell-bent, I'm gonna do that for my entire 30-year career. I punch that in, and it comes out, I need 4.1 million T1s per site at the end of that 30 years. Yeah. Right? Here's a neat thing, neat trick. Actually, here, let me show you what I mean by hockey stick curve. I should have. Another neat trick here. So you want to graph what this looks like. If you do 1.6 to the x, draws a nice little curve here, right? It starts growing slow, 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 and all of a sudden it hits and just goes whack straight up. And if I zoom out, you can see it just goes vertical. Right? And that's why they call it a hockey stick curve, because it looks like a hockey stick. You start a little bit, kind of, it tilts, and then just goes straight up forever. Right? That is what our growth curves look like. It's not double, you know, it's not linear. It's kind of slow, slow, so slow, wham, slam into a wall. There's a couple of tricks to that when we're thinking about our equipment and our sizing and our approach to that. One of the interesting things, you can take infinity times by 1 divided by infinity, and you get 1. So as long as you have something that's growing smaller at the same rate that you're growing up, you're gonna be okay. And so here's a real cool example is 17 years ago, I looked this up, we were buying 10 megabits of ISP service at $350 per megabyte. That cost me $3,500 a month. 2 years ago, I had a 10 gigabit circuit of ISP at 35 cents per megabit, $3,500 a month. One's going down at the same rate the other one's going up. I multiply them, my budget stays steady. As long as we keep doing that, we're okay. If we keep growing and the price doesn't drop the same rate, I'm in deep, deep, deep trouble, right? Same thing with all the other equipment, disk space, memory, CPU power, anything that we're looking at that's growing exponential, we've got to be really careful to make sure the cost per unit's going down at the same rate, or we got a serious problem. One of the other things that's kind of interesting in this too is a lot of times if you look at inverse logic, you can actually come up with some neat tricks, right? Because if I take 1 divided by infinity, it goes to 0. And we can actually kind of pull that trick off sometimes when looking at management and a couple other cool things. So pre-CTA, we had a consortium, a different consortium with different players, and we had 1 router, 2 ISPs, and when we wanted to make a routing policy change, we would go through and edit every policy by hand. Not that big of a deal because we had at most 2 circuits per ESD coming into it, and we had most 2 circuits going out to the ISP, so only a couple things we need to tweak. When we created CTA, the director said, we want 6 routers, 6 ISPs, which is more than 10-fold complexity. And we were gonna have fewer staff to manage it. I thought, crap. So I started thinking about going, there's gotta be some way of dealing with this. So I started looking at big providers, someone who's doing more than 10 times my size, how do they do it? And they flip their logic around. When it comes down to doing the routing policy, they hard code it and they manipulate it at the source. So rather than manipulating my routing parameters to an ISP as it goes to the ISP, I just go to wherever the IP originates and I change the parameters there and it just goes through my network. I don't have to change any policies, I don't have to touch the ISP provider, which has some really cool things in that I cut my actual changes down at least in half, because I don't need to modify 2 at a minimum, I just need to modify 1 thing. And I can prove it in advance. I can go through and be very, very careful to make sure my policy's correct. And at that point, I can just trust it. So way less error prone. And of course, I'm manipulating just 1 route at the source. Before, we were manipulating everything going through that ISP. So if I made a mistake there, it took everything out. This, if I blotch it, I'm blotching 1 route. Right? So much, much less risky. And a cool thing about this too is anyone at BGP peers with any of my routers can manipulate their own routing because they can use the same tricks I do. So anyone like Portland Public Schools or Beaverton or Hillsborough, any of the big school districts is doing BGP with me, if they, for whatever reason, want to manipulate how their presence on the internet works, they want to shift their traffic from one ISP to another, set a black hole route or something, they can do it without even calling me, right? Because they're the ones originating the routes. They can manipulate the same flags to manipulate how it goes through the network. Very, very cool. Okay. Question, anyone here actually know BGP and know what the hell I'm talking about on that? A couple of people. Okay, so this is how you do it, right? On Cisco, when you originate the route on your network statement, you do a route map and you attach the communities to it. That's it. If I want to change, so in my routing policy, instead of saying match on this prefix, I will say match on these communities. And I just set the community when I define the route, and that adjusts the behavior of the traffic. So it's basically like source routing, right? At the source, I'm defining how the routing through the network's gonna go through. We're a Juniper shop, we just attach it directly. Wherever I set, like on my firewalls or somewhere where I have a static route, I just attach communities to it, off it goes. And it's also a very big, complex network, and sometimes I don't really know exactly where a route's coming from. And rather than going to look it up, all I have to do is just trace it through the network. Wherever I eventually hit where the route originates, then I can manipulate it. So it comes in pretty handy on that too. All right, moral of the mathematics, right? Be prepared to change your technologies every 5 years. You're almost going to have to do it every 10 years. And if you try to run T1s your entire career, you are a madman, right? As long as as long as your cost per unit stays in line with your growth, you're okay. Ooh, that came through bad. Okay, right, different technologies. Yeah, I won't bother. Different optimal strategies. Every time you're changing technologies, things are a little bit different, right? So also be careful not to try to do the same thing over and over and over again. Think about it every time you do something different, because a T1 and a gig aren't the same thing. 100 gig and a gig is not the same thing. If you try to do the same thing over and over again, you're probably missing some opportunities, okay? This is one of the ones I'm working on now. As I'm changing my technology, we're getting dark fiber. Dark fiber, you can do different things than lit fiber, right? So we're gonna get into routing with light. So you may have heard some from time to time people talk about doing wave division multiplexing. Basically it's tricks of light. You can take different colors coming into a prism, focus it into white light, at the other end split it back apart again. So basically you can get colored lasers, each one of these say like 10 gigabit, run it through a single fiber, at the other end break it back apart again. So using the cheap commodity stuff, this isn't a 10 gig, this is now 400 gig or 800 gig, depending on how big of a mux I put on it. So you can get 40 colors, 80 colors. You go with a large scale commercial solution, you can get 160 colors or 320 colors. Not that we could afford it, but you can just get terabits and terabits and terabits out of a single fiber, right? So you can think of it as compression. You can't do this with a standard Metro Ethernet solution. You can if you have dark fiber. So if you try to do your lit service ideal on top of dark fiber, you're missing this, right?
So are these just different kinds of SPDs?
Yeah, they're colored lasers. They're all slightly different wavelengths. And so they call them lambdas or channels or something like that. So you have channel 20, 21, 22, 23. So you shoot in 20, it gets put into the white light. At the other end, it pops out on the channel 20 on the other side. And so it works both ways. So you get a virtual circuit. And they're all independent of each other. And so the other cool thing about this too, once you got this in place, right now you can get colored optics that are 1 gig, 10 gig, or 25 gig. And so if you have one particular circuit that you want to move from a 1 gig to a 25 gig, all you have to do is replace the optics, because it's the wavelength magic that happens, not the throughput. So kind of cool. So once you've got it in place, you just start swapping your optics out, and you've got a whole new circuit. You're not doing anything else, right? So like I said, this kind of comes through as like compression. This is really cool. This is called optical add and drop multiplexing, and I have no idea how to really demonstrate this here. I'm gonna try my best. All I can say is just go Google it, right? So what these things do is you can literally route with light. And so you have a fiber come in and a fiber go out, right? So this is, you can barely see it on here, but this is your input and that's your output on that side. So you can make a ring like all your schools with a single pair of fiber. You have one of these at every school and you tie them into out, all the way around. These, which you can just barely see on here, these are channels. These particular colors get pulled out of the white light or added back in. Everything that's not one of these just passes through untouched. So this is a light router. And it requires no power, no moving parts. This is they run, you can get them as low as about $150 per channel. So if you're gonna do just one wavelength, it would be $150 for something like this. They call it east and west. It's kind of divided in half. And so I have like a channel 22 here and a channel 22 over here. Light coming into this one pops out here. Light comes in this way, pops out here on channel 22 only, no other channels. Same thing on the other side. And so what I've effectively done is take my one strand of fiber. Now I have two circuits redundant because one goes one way around the ring, one goes the other way around the ring. And I can do that for every site. If I wanted to do not a full ring, but I wanted to have a central location where everything comes back to, I could do two standard muxes. Right? It just has all channels on it. And one will go one way around the ring, one will go the other way around the ring. Right? All kinds of really, really cool things you can do with this. It's dirt cheap and almost infinite bandwidth. Right? Very, very, very cool.
You could conceivably put like 40 gigs on each channel if you wanted, right?
Yeah, there's a couple of things, yes. So these can be, this is, your options are 10 gig, well, not per channel. Your options right now are 10 gig or 25 gig. If you get a 40 gig circuit or optic or a 100 gig circuit, it is not really, like a 40 gig is not 40 gig, it is 4 10 gigs. So they're doing the same trick, they're doing this trick, but in the optic, right? Because it's 4 different colors at 10 gigabit, and 100 gig is just 4 25s, right? So you can't do 100 gig on one channel, but you could do 4 channels at 25 and get 100 gig out of it. But in this case, it's actually 200 gig because you get 100 one direction and 100 the other direction because it splits it in half. Extra, extra cool.
So we're newer using quarter-wave vision multiplexing, the same stuff. And I would add that in your planning, know what the loss levels are on the fiber infrastructure, and also understand what the loss is in the OADM. When you try and pass wavelengths through the enclosure, make sure that your budgets are still in line.
And the other fun thing is, especially, this is not a problem with the muxes because you have all your inputs at one place. With these, you're injecting lasers at random places around the ring. So at every hop, every channel is going to be at a different power level by default. If you get it too far out of whack, it makes a mess. And so while this is really, really cool and really, really cheap, it is also really, really different. And you have to go figure out what you're doing before you go large scale on it. So like to the power levels, what you do is they have like little adapters that are basically resistors. So you can normalize any input to make it all line up. It's pretty trivial to figure out once you've done it. And then they have amplifiers for if you have too much loss, you stick an amplifier in. And the amplifiers are really super cool too. This is how they get undersea cables to work. The amplifiers don't care what the signal is, just whatever's coming in, it just sends more out. So it doesn't matter what channels you're using, what the data is. If one's 1 gig, one's 25 gig, it doesn't care. It just replicates whatever's there, so there's almost no configuration.
Are long-range optics an option in this scenario?
Yeah, there are,
PRs or something?
yeah. In fact, that's typically the way it's done, is you usually get a 40 or an 80 kilometer optics. If you buy third party, the pricing varies. If you're, I should toss that in also. If you're trying to buy colored optics from your vendor, probably not cost effective. If you buy third party, not bad. The cheapest I've seen for shorter haul ones are about $300 a pop, and the long range ones are usually about $450. You can also get tunables, because you have to order it by the color, and they also have ones which makes sparing tough. So my strategy is going to be, once we start doing this, is just have lots of extra channels so I don't care if I lose 10 gig, right? I can replace the optic whenever I want, and we'll also keep spares that are called tunables, where you can adjust the frequency of the laser. And they're a little more expensive. They're $2,000, $3,000, but I only need to keep 1 or 2 around and use it as a spare, in case of emergency. So again, one of those things that's a little different. It's wildly different, but it's a type of thing you wouldn't think about if you're just trying to replicate what you've done in the past. And the other cool thing about this is a lot of times when people are talking in terms of fiber, they're doing large fiber accounts, they're doing their own build. A lot of times we're only going to get 2 pair. And how do I build an entire network out of 2 pair? I use these. I can get as much or more capacity, and it's naturally redundant by the way it works, because half the traffic goes one way, half goes the other. Boom. And all I need is 1 pair. Very, very cool.
You need to be on a ring for this now.
Yeah. That's the other thing too. If you're looking at fiber, right, theoretically, it's number of fiber miles you're paying for, and the cheapest possible way of doing it is to connect each site directly to each other. If you do a hub and spoke, it's not going to be possible to do redundancy. If you're going to do redundancy, and it uses a lot more fiber, if you're going to do redundancy, you're going to have to do a dual hub and spoke, so you're going to be buying more than twice as much, so you end up with a lot more fiber. Or if you can build directly from school to school to school, then you can use something like an optical add-drop multiplexer to build a ring out of it. Now, of course, you could always do it lit, where you could have a router at every location that passes the traffic back and forth, run OSPF or something like that, but you're limited to whatever the bandwidth is, the optics you put in, right? So if you went 100 gig, it's going to be a 100 gig ring. These, starting off with this cheap stuff, I'm starting off at 400 gig. So, it's definitely, I think this is a much more interesting way of going about it, especially since this is not powered. So if I lose power to a location, every site downstream of it is not affected. Unless it's the one site that has the amplifier, but it's still redundant, so everything will go around the other way. Life will be okay. All right, another thing, simple layer 3 routing tricks, more traditional. Hopefully you guys are all doing this. All your dynamic routing protocols, OSPF, BGP, they're slow to detect failures, and if you have a problem, your network's going to stutter. A lot of them are 90-second timeouts. Your phone system's going to suck. People are going to be mad. Bidirectional fault detection, we run this everywhere. If your equipment supports it, do it. You can do sub-second failover with any protocol that will do it. It's basically like a pared down OSPF optimized for this. It just sends packets back and forth as fast as it can. And whenever it sees a problem, it sends a signal to the routing protocol going, hey, go check this out. And so instead of waiting for that timeout to happen over 90 seconds, it happens in like 1/10 of a second. Way happier if you do that. Very easy, just go figure that out and do it. And the other thing is occasionally things blow up really badly. Use floating statics if you can, right? All you have to do is put a static in with a heavy weight on it, so it's only used if everything else is blown up. This will occasionally save your butt when things go really bad. It's really easy to do, and it has no effect whatsoever if everything's correct. So if you do a lot of routing, think about that one, right? Here's another interesting one, right? I think about price performance features, you get to pick two, right? A lot of times we're making tough decisions about how big of something we should buy. You know, does it have all the bells and whistles, you know? Do I buy a cheap one and spend my money elsewhere? You know, I struggle with this one a lot, right? One of the problems I got right now is once I start muxing dark fiber, I suddenly gonna need a lot more 10 gig ports. Because, you know, Beaverton or Hillsboro or something like that may ask for, you know, 10 gig ports or something ridiculous. I don't have 10 gig ports in my router. What am I gonna do with this, right? So I go and look, and if I get a bigger version of my real router, I get 10 times the price, half the ports versus a layer 3 switch is 1/10 the price, twice the ports. The only drawback is it doesn't do full BGP tables, and traditionally we've always ran with full BGP tables. So it's like, crap. You know, it's like this one feature that is gonna cost me, you know, hundreds and hundreds of thousands of dollars. Do I really need it? And so we went through and proved that we actually don't need it. And we did a plan B in case I'm wrong, I ever do need to take a full internet routing table. I'm just gonna fire up a route reflector. And for my routers, I can use a default route, and whoever downstream of me needs the full tables, I can pass it on, but my equipment itself doesn't need to support it. So go through, model it, test it, works fine. We also hedge our bets in that we actually have 2 routers. We only did this on 1. We still have the big traditional route until we're really sure we don't need the full internet routing tables. But one of the actual really cool things about this is the lack of features is sometimes a feature that will save your ass. BGP conversion time, if you're taking a full internet routing table, unless you have a really good expensive router, can be problematic because pulling those hundreds of thousands of routes in and out will bog it down and cause you problems. If you're taking just a default route from upstream, that's instantaneous, not a big deal. BGP bug crashes. So when we first started the CTA network, we had one of our vendors was late getting our redundant circuits in place. And it was gonna look like a 30-day window where we're gonna have just one service provider, and we were not happy about that. So I was out asking around for someone to bail me out, and Nero says, what do you know? We got a free gig. We're just about to shut a circuit down. You pay that 1 month extra, and you can use our gig. Like, cool, right? So we fire this thing up, we plug it in, and the very next day was one of the big BGP update bugs came out, and it crashed my router. If I did not have redundancy, wouldn't have skipped a beat. The day the entire internet crashed, it crashed me too. If I was not taking full routes, wouldn't have happened. And it's really kind of interesting to think when you're taking the full internet route table, anywhere on the entire planet that's running BGP is configuring your device. Every time anywhere in the entire world makes a change, it gets copied to you. It's really kind of fascinating to think about, and occasionally really bad things happen. Every single vendor has had a bug that has caused their router to crash because someone pushed a bad update and it's knocked the internet offline. Won't happen if you don't actually accept those routes. So sometimes that's a feature. All right, enemy of the state. I hate stateful devices. I used to love them when I had just my own little network. Now I have lots of networks, and I'm trying to move things back and forth. Firewalls, web filters, all that. Hate them. They're the bane of my existence. They are a single point of failure by design. The performance is dismal. They're horrifically expensive, and they're context sensitive, right? If you're natting your servers, you have a different DNS view on the inside and the outside. Huge amount of grief. Just put the public IP address on your server, and then you got one view, and you don't have to screw around with worrying about you got your context right? So no NAT. We're moving our infrastructure over to IPv6 because of the stupid firewall NAT problem. I got my infrastructure between dozens of firewalls. Makes my life hell. IPv6. Real networks, when you're looking at the Googles and the Amazons of the world, they don't use firewalls. They just don't do it. Any filtering they do is going to be router ACL. They might do it in their load balancer. They'll have something that's not a traditional firewall. They just don't scale. You can't run Google on a firewall. Doesn't work. This is the one I'm thinking on now, thinking long and hard about. I'm sure lots of you heard me talk about this yesterday after well into the social hour. If you're gonna get stuck with a firewall, because although I'm gonna evangelize we get rid of them, no one's gonna buy into it because that's too scary. Most of the time, we have the firewall in front of this VM farm. And once I get my dark fiber in, I can start failing over VMs between data centers, right? Because I have infinite bandwidth, no latency. Problem is I got these damn firewalls bolted in the rack that aren't, it's just, it makes my head hurt trying to figure out how to make all this work. And then the light clicks in going, damn, I'll just run it as a VM and I'll just move it with the farm. Right? Still a single point of failure, but I'll have it on redundant infrastructure and I just move it around. So that's when we get back, we're gonna make that work. And if you were here last year, my other thing I hate is stateful web filters. We've all moved almost everything over now to DNS-based web filters, which is naturally redundant. I don't care where it's coming and going, it just works. Life is much better. I'm sure you heard that from the other presentations from folks I got. And my last slide here, the root cause of all these problems is us, right? We're the problem. Network administrators have destroyed more networks than disasters, fiber cuts, fires, hardware failure, software bugs combined. It's us being tired and grumpy and making bad design decisions, typos, mistakes, and we're the ones that cause problems most of the time. Don't forget about redundancy of staff. I was just talking with a couple IT managers. Their last big outage they had was the day that their one network administrator had gotten married and was on an airplane after the honeymoon. And they penciled out, they managed to save themselves, but it was almost a multi-million-dollar deal because it was a large school district and it was a grading day that had penalties from the union if the network's not up. That day, right? So don't forget about redundancy of staff. And also, in general, like I said, just try really, really hard to keep it simple, flexible, debuggable, and comprehensible as you can. That's another thing about when you're talking about staff is you may know it, but the next person that comes in or whoever's backfilling you may not get it. Try really hard to make it comprehensible. And you might throw your back out, not sleep well, have a problem after being at the social hour for a while, and then you gotta fix it, right? So you may screw yourself, let alone someone else. Be really, really careful of that because that causes problems. And I think with that, yep, that's my last official slide. Go for it, Jamie.
So I had a question. When you're talking about getting rid of firewalls, you're just talking about in front of your server, not necessarily your client?
Okay, so yeah, so the question is are you talking about just in front of the servers, not in front of the clients? Okay, also been thinking about this a lot. So the servers are obvious, right? If you move to router ACLs, which all happen at line speed, and you put the real IP address on the server, you don't need a firewall, per se, right? If you're just doing standard, just these ports, these IP addresses, you're not really getting much above the ACL anyways. And because it's not stateful, you could fail over through different infrastructure. And as long as the packet makes it to the server, you're okay, because it's the server, it's maintaining that state, right? If you're doing NAT, you got a problem. And so the only way I can really think about doing this is don't do NAT, which seems flippant, but since my infrastructure is IPv6, all I have to do is go in and turn on router advertisements, and I automatically push IPv6 to all my clients. And the majority of the things that people really, really care about are all IPv6 now. Google, yada, yada, yada. It's all IPv6. And it's a different protocol, so I can route it differently. So I can have a different default route for IPv6 than IPv4. So I could get rid of at least 50% of my traffic I could get rid of from a firewall. My firewall dies, Google would still work. So I've been thinking long and hard about that, but it fails the obvious test. So I want to do it. When I sit down and I try to talk people into it, they're going to say no, right? But it's kind of cool, and I want to do it.
What about other things like malformed packets? I know some firewalls, we're going to look at all this data and try and block it because it doesn't look quite right.
So you have at some point in time, you're making a decision on what, I mean, you're gonna have to make a value decision, right? Are you gonna optimize for the weird edge case, or you wanna optimize for making your network as reliable and as fast as possible? If you wanna make it as fast and reliable as possible, you don't give a rat's about whether or not there's an occasional odd packet. You can do basic sanity checking and hope whatever is at the other end sorts it out, right? Which is actually another interesting thing too, and when we're having these conversations, when we're thinking about this, also, it used to be everything was inside, right? That's not the case anymore. We're sending devices home with kids. The teachers are bringing their own devices in. We really don't have an inside or outside anymore. So we really can't put all of our protection in the firewall because the firewall only covers a subset of what's going on. Most attacks really are not malformed packets. They're gonna be application layer attacks, phishing, yada, yada, yada. Your firewall, if it's encrypted, right? HTTPS is not gonna save you there. So like I said, it's really a value decision, and for the larger school districts, where we're getting right up to the edge of what we can do for a reasonably priced firewall, we're gonna have to make some really hard decisions, because getting a real 10 gigabit per second through a firewall is really, really expensive. And I can buy, like, I mean, for like $1,000, I can buy a layer 3 switch that will push like a terabit per second or something outrageous, right? Like $1,000 just drives me crazy, but you know, yeah, it's a tough one, and I imagine we're gonna keep pushing it as far as we can, but if we're someone like Google, the way, at that scale, the only possible way to do it is not to care about it. Something has to give, and that one is probably far enough down the edge case that we'll have to give there before we give in on spending $1 million on a router or a firewall to tackle that specific problem. That's my bet, but again, I'm also the guy going, hey, we really should get rid of firewalls. And when I sit down like with your boss and say, we should get rid of firewalls, he's gonna look at me really funny. So I'll just keep saying it, keep saying it, keep saying it, and 5 years from now, we're all gonna hit this problem and say, I told you so, and then we'll go do it. By then, everything will be IPv6, and we'll be good anyways.
What's your thought on VRRP?
Yeah, you know, it's one of those things. I actually, for the most part, we're not using that anymore. We're mostly, any place where we're doing something like that, we have a lot of virtual chassis or something with redundant routing engines in it. Can you guys think of anywhere we have VRRP running? You know, it's one of those things that, yes, it can save you. It can also bite you. You know, it's the standard complexity versus redundancy. You know, if you've been using it, it's working fine for you, go for it. But we've over time kind of drifted away from doing that. Actually, you know, think about it. Most of my infrastructure now, because we have everything BGP on the outside and OSPF on the inside, I don't really care necessarily if a device dies. It just automatically reroutes around it anyways, right? But good question, because I actually haven't thought about that in quite a while. We also don't do MLAG anywhere either. We're not doing cross-chassis lags. We're either doing it on virtual chassis or we're just not doing that. We did do it. We had one system that we were doing it a couple years ago. Blew up, and I just shut it off and stopped doing that.
Well, my only comment was the course wave stuff that you were talking about essentially gives you lots more options around layer 2 everywhere. You have the fiber, which then means those networks can appear anywhere in there. VRRP, they could be used to make the default route on any of those networks appear at any of those locations.
Yep, and another thing too is Anycast. Right? One of the Anycast is basically all you're doing is advertising the same IP address out in multiple places, so it just automatically picks up whatever's closest, right? When you go to Google, you go to 8.8.8 for as a DNS server. It's not one server, it's just whatever the closest one happens to be. And we actually use that trick for our web filtering. If anyone tries to bypass it by using Google, I just make my web filters. It'd be 8.8.8 and 8.4.4. INE cast form, I'm good. Right? So there's all sorts of little tricks like that you can do. All right, any other questions? Go.
I think it was like second or fifth slide, it was inverse.
Oh, inverse logic or something like that, trying to flip something.
Say that one more time, I'm kinda
Okay, so the actual math part about it or just thinking about it part of it?
thinking about it.
Okay, so let me show you, yeah. All right, so I'll show you these are our actual live routers here. Okay, hang on a second. I'm gonna think about this one for just 1 second. Okay, I got what I'm gonna do. Okay, so I'm gonna go, okay, so this is my second, this is actually the switch. This is my shiny new layer 3 switch to replace my god-awful expensive router. And I have Cogent attached to it, and I can't remember the IP address. I gotta look. Show configuration protocols, BGP, group, Cogent. All right, so it's 38. All right, if you look up here in the top here, let me put this up at the top. I've got a policy called, we're gonna do Cogent export. We're gonna show how things go out. Right, and I've got this show configuration policies, policy options, Cogent export. So I've got this policy that matches communities. Basically it says, hey, if I have this community called Cogent Pad 1, I'm gonna set it as Cogent and I'm gonna take my AS path and add 1. Right, so if someone wants to wait, they want less traffic to go to Cogent, the way BGP does it is by the number of AS hops in the path. So you can trick things to go one way or the other, or at least try to trick it, it's just a suggestion, by adding your own AS number multiple times, right? So we're gonna do 1, 2, 3, whatever, these are predefined. So like if Portland Public wanted to, their traffic not to go to Cogent, they could just remove the Cogent community completely from their advertisement, or if they wanted to pad it, they could set my Cogent Pad 3, and it will still advertise out, but it'll append their AS number 3 times to it, so the traffic will be less likely to go that way, right? And then down here, I basically say, hey, if I'm matching the community Cogent, advertise it, and then I delete a bunch of the other communities, so I'm not polluting the internet with a bunch of crap no one cares about. Otherwise, I reject it. So that's my policy. Basically, if I have that community of Cogent set, which I set at the source, it will flow through my network because every router basically has these type of policies saying, allow, if the community of Cogent set, send the route onto the next hop up towards Cogent. Right? So I set it at the source and it just automatically follows through the network, hits this, goes down and says, okay, I have Cogent set, I'm gonna allow that prefix out to Cogent. So I will show you here the actual advertisement, show route, advertising protocol, BGP, this guy, whoop, crap. Show route, advertising protocol, BGP. Okay, so here's my advertisements, and here's where I have to think about this one for a second. I'm not gonna screw with anything important. I was gonna go in and like set MESD's route here. I was gonna change the padding on that one, but instead I'm just gonna take a route I know it's not in use. So I'm gonna go to MESD's firewall. Oh, come on. Here we go. All right, edit, routing, options, static, route. Whoop. Edit, routing, options, static. So, let me find one that has a community here. Whoop. Show, route, 198, 236, 64, 0. right? So here I have a static route set pointing back into my network, and I set all the communities that I want. So if I wanted to if I wanted to drop Cogent, I know that this right here, that's Cogent's, I can just recognize it from this. They're defined elsewhere. But I know 174 is Cogent, so if I delete that, my advertisement to Cogent would go away. Instead, what I'm going to do as a quick hack, I'm going to pick a network that I know I don't care about. I'm going to do set route 198.236.69. 69.024. Next hop. And then, so I've defined a static route on the firewall, which is a single point of failure. So this is where my route's going to originate, and I'm just going to set this community on it. Ooh, yeah, come on. Grab that community. Make sure I'm not doing anything stupid. Oop. Okay, that should be all right. Commit confirmed. We'll set it for 2 minutes. Cool thing on Juniper stuff, right? So you do like a candidate config. So it's actually not live until you commit it. I'm doing a commit confirm, so this will actually stay, that configuration will stay there for a couple minutes, and then it'll get pulled out. So I won't remember to have to remove it later. So once it's done, which this on firewall is kind of slow. Now when I come over, now that route, since this is talking BGP to the upstream, that route will follow through the network, pop out, and show up down here at Cogent now. Except for it doesn't. Well, anyways, if it wasn't a live demo, this would have worked perfectly.
What's any downside?
Besides the fact that people, you kind of have to show people how it works, right? It's not, if you haven't done it this way before, it's not obvious, because usually how you do it is when you're setting your configurations, you're editing your policy right where you're advertising to the ISP. This is where you're influencing how your advertisements go out. This is the option, going way to the other end of the network and making the configuration change there. So you kind of have to walk, and you get someone new in that's never done that before, you gotta go, this is how you do it.
From like a logistic, I mean, like from a functionality standpoint, this seems like a better approach.
Yeah, so if you're someone like, I think I got this from like Akamai. Some enormous network says, if you're gonna do it this way, right? Because this scales infinitely, right? Once you've got it down, you can have your one golden policy, you can copy it everywhere, and you have one touch point that'll influence everything through the entire network. If you're someone like Akamai or Google or something like that, and you're trying to change a policy by editing every router to make it happen, it's not possible, right? This is trivial. And once you've done it a couple times, it's kind of obvious, and you're just like, oh. And especially for someone like one of the things I like too is self-documenting systems, because it's complex enough, even if I have it documented, it'll take me longer to go find the document, figure out, reading through it, where the hell something's at, right? Because we even amongst ourselves, someone occasionally say, what the hell is this IP address doing here? It's like, well, because we needed a block, so we moved it over here. Especially this will be really, really bad when we start failing over between data centers, because then our IP addresses can be anywhere, right? So you can't look at an IP address and go, oh, that's Northwest Regional, it must be over here. Yeah, maybe not. And all I have to do in this scenario is I want to modify how the route's happening. All I have to do is just follow the route through the network, and it'll lead me right to wherever it originates, and then I can modify it there.
Because of that tag.
Well, it's not so much that is you just have to go, if I want to know where that route is, and I guess I have a route summarization turned on, which is probably why that didn't show up. But if I like to show route 198.236.69.1, it's going to tell me, here's your next hop, right? I just have to hop through the network like that, right? So I've got this guy, and here I just do SSH. And why is it not going there? Come on. Go look at this one. I killed my SSH. Okay, anyway, so I can hop through the networks. Apparently I don't have my SSH key on that one, and it's a horrific password, so I'm not even gonna bother trying to type it. But that's what I mean by all you have to do is just follow the route through the network. It tells you where it's at.
Thanks for explaining.
Yeah, and as I said, a lot of times if you're thinking about things, when you get stuck, just try to think of it from the other direction, right? Look at a layer higher, a layer lower. Is there some other way I can do this? And sometimes something just pops out and go, oh, that's obvious. That solves my problem. Yeah. Okay, any other questions? Yay! Okay. Hang on. Thank you all.